So, are you ready for this big statement here? This chapter is the last chapter before the AP exam. Okay? All right? That is not the last chapter of material that we will be learning, but anything beyond this chapter that we learn is material that will not be on the AP exam, so this is our last bit of examable material, okay? For those of you that are in physics or have taken physics, you will see some crossover. How many of you have done circuits or are doing them now? Okay, this is not a physics class, but you'll see some topics that you may have discussed in your physics classes. So, electrochemistry, guys, is exactly what it sounds like. It's the conversion of chemical energy from a chemical reaction and converting it into electrical energy. So taking the energy associated with a chemical reaction and using that energy to power something, okay? So you're using it as a power source, an energy source. And it's not all reactions that can be in an electrochemistry setting. Not all chemical reactions can you do this. What kind of reactions are we looking at? We're looking at redox reactions. So we need to review those terms. Okay. I have my own mnemonic device to remember the definitions of oxidation and reduction. This is mine. Okay. Leo the lion says grr. Some of you, other teachers use, I think it's like oil rig or something like that. Does that sound familiar to anybody? Something? I don't know. Oil oxidation is loss, I think. But this is mine. Okay. The element that is oxidized from left to right, from reactants to products, loses electrons. Okay. The element that gains electrons from left to right, reactants to products, is the element that is reduced. Now, just to make sure that we've got this down, electrons are negatively charged, right? Say yes.
Yes.
Okay, good. If something loses electrons, which are negative, what should happen to the charge? Or a fancy way of saying charge is oxidation state. From left to right, should the charge be increasing or decreasing if something's oxidized? Increasing. If you lose negativity, you become a more positive person. It's terrible. That's terrible. Wah, wah. Okay. So, need to remember these terms. And where we have seen this before, and we're going to see again, is in the setting of half reactions. Okay? A half reaction involves an element or an ion and balancing its charge with electrons. Okay? And electrochemical reactions always involve one thing being reduced and one thing being oxidized. I mean, think about it. They're called redox. They're not called read or ox. You have to have one of each. I want you to notice something about these half reactions. If a half reaction is written as a reduction, you will always see electrons on the reactant side. Okay, reduction has electrons on reactant side. Oxidation half reactions are always going to show electrons on the product side. We've seen half reactions before, although it was a long time ago. That was first quarter. And what we did then, we'll do again in this chapter, we add them together. Do you see anything that can cancel out? Electrons. Okay? And they have to cancel out. We never will have electrons left over in our, this is called our overall reaction. Okay? So this is the overall electrochemical reaction, which is made up of these two half reactions. Now, what kind of a setting are we going to see this in to make this an electrical situation? We're going to see something like this. All right, let me explain to you what this graphic is showing. Okay, I've got a beaker here, this yellow shape here, okay, this yellow bar would be representing a piece of zinc metal, pure zinc metal, which is immersed in a solution that contains zinc ions. On this side, you've got a beaker, you've got a bar, this would be a bar of pure copper metal, which is immersed in a solution that has copper ions floating around in it. These two metal bars are connected with a copper wire. Okay? Now, if you look at the half reactions we just had on the previous slide, the zinc half reaction is occurring here. The copper one is happening here. Which one, please look back at what we wrote down, which half reaction, the zinc or the copper, has electrons on the product side? The zinc, okay? So this half reaction is producing electrons, releasing them, giving them away. Where are they going? They're going to travel through this wire. So I am going to label this diagram a little bit here. Electrons are being produced from this half reaction. Produced, released, given away. They travel through the wire to this half reaction, which, if you'll notice, has electrons being taken in as a reactant. And guys, when you hook together two reactions, one that's giving away electrons, one that wants to take them in, electrons will flow spontaneously. And the flow of electrons, ladies and gentlemen, is electrical current. It's electricity. Anytime you have electrons flowing through a wire, that is electrical current. We're using chemical reactions to create electrical energy. But there's a problem with this setup here. And those of you that are gifted in physics, I'm asking for your help here. If I hooked these two reactions together, connected with a copper wire, would I get a flow of electrons? Absolutely, yes, I would. However, this would only run, I would only get electricity for like a second, and then it would stop flowing. What's wrong with this picture? Why wouldn't electrons just keep on flowing, 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 flowing? What's the problem? It's not a complete circuit. You're absolutely right. Okay? What's happening here? Electrons are flowing from left to right here, from the zinc to the copper. Right? I'm getting a big buildup of negative charge on this side, because that's where all the electrons are going. And if this side is becoming very, very negative, this side is becoming very, very positive. I need something to fix that imbalance. And I'll show you what's going to fix that problem. Okay. Now guys, there's a lot going on in this picture. We're going to just take this picture piece by piece. Okay? But it's the same picture as what we had. It just looks nicer. Here's my bar of zinc. Here's the zinc half reaction taking place. Here's the bar of copper. Here's the copper half reaction. Here's the copper wire. Notice they've even labeled it. The electrons are flowing. To fix that incomplete circuit, guys, let's focus on this part first. We put in what's called a salt bridge. This completes the circuit. Now, what flows through a salt bridge? Well, let's make sure we've got this. Electrons flow through the wire. What flows through the salt bridge is not just ions, not just any ion, but spectator ions. What does that mean? An ion that isn't participating in our reaction at all. Remember what the problem was. Before we had that salt bridge, we had a big buildup of negative charge over here. Well, how do we fix that? How about if we take some of that negative charge and have it flow away? Or what you could also do is have positive charge flow into it. Okay? Both of those things will prevent that big imbalance of charge, big negative, big positive. The salt bridge helps maintain a charge balance in this whole setup. And by the way, this whole setup has a fancy name. It's called a galvanic cell. Do you know that is the term, fancy term for something very, very simple that we use in our everyday lives all the time? What is this? It's the more common name for a galvanic cell, something that produces power for us. A battery. This is a battery, ladies and gentlemen. This is how batteries work. Okay? Now, please do not go home and say, oh yeah, we talked about batteries in class today. I want to see how batteries work. And so you decide to crack open a Duracell D battery. Please don't do that. Okay? Battery acid is sulfuric acid. Okay? It will eat your fingers off. It will take the fingerprints off of your fingers. Please don't do that, okay? But if you were to crack open any kind of a battery, I mean, obviously you're not going to see like two teeny little beakers and little solutions. No. But you would see separated compartments that are connected with wires, okay? This is essentially how batteries work. You could get power out of this system, okay? Now, let's talk about a couple other things. Look back in your notes. The zinc half reaction, was that oxidation or reduction? Which one was that?
Oxidation.
Okay, it was oxidation. I'm just going to write that under here, which means this one was reduction. Wherever oxidation is taking place, this would be called a half cell. So like half of your galvanic cell, we call this half cell the anode. Wherever reduction is taking place, we call that half cell the cathode. Here's an easy way to remember this. Okay, wherever oxidation takes place, that is the anode. Please notice both of those words start with vowels, whereas these both start with consonants. Or sometimes you'll hear people say an ox and a red cat. Whatever. Whatever's going to help you remember. Wherever oxidation is taking place, that's the anode. Wherever reduction is taking place, that's the cathode. Okay? Something else, and I want you to write this down. In this picture, electrons are flowing from anode to cathode. And guys, that is always the case, no matter what, no exceptions. Electrons always flow from anode to cathode. No exceptions. get to say that very often. The last thing that I want to call to your attention, because there's so much going on in this picture, is these blown up images of what's going on here. Okay? On this zinc side, look what's happening to this bar of zinc. Solid zinc is being converted into its ion form. This bar of zinc is actually disintegrating over time. The mass of this bar, as this galvanic cell runs and runs and runs, the mass is actually decreasing. This bar is shrinking. Whereas look what's happening on the other side. Copper ions are becoming solid copper. This bar is increasing in mass. Okay? If you started with a bar that was 10 grams and you ran this cell for days and days and days, or however long it would run, if you measured the mass of that bar at the end of those days and days, it would be greater than it was before. This one would be lighter than it was before. Okay? Just want you to be aware of that. Okay. We're going to put some numbers to this. And there's a term that we use a different term than physics does. In physics, have you guys heard of a term EMF or electromotive force? Okay. In physics, this force that we're going to talk about, they call EMF. In chemistry, we call it a potential. It doesn't matter what you call it. It doesn't even matter how you think of it, guys. It's a force moving electrons through the wire. It doesn't matter to me if you think of it as the electrons being pulled by the cathode, or if you think of it more as electrons being pushed from the anode side. I don't care how you think of it. But it's the force moving the electrons through the wire. We are going to call it potential. Okay. You'll see it written usually like this. Okay. Sometimes you'll see it written with this really fancy curly QE. Sometimes it's written like that. But essentially, guys, it's a voltage. It's measured in volts. Okay. So we're going to put some numbers to this. You have a book in front of you, yes? Okay. Please go to page 841. 841. Page 841, guys, has a chart. And we're going to use this chart. We're going to use a bigger one in the back of the book as well. Okay, but look at the title of it. It says Standard Reduction Potentials. If you scan your eyes down this chart, they're half reactions. And do you notice that electrons in this entire chart, they're always on the reactant side? Do you notice that? Okay. Well, they should be. They're all written as reductions. Okay. You have the potentials going down the left-hand side. It says E and then a little subscript RED. That just stands for reduction. You'll notice the chart is organized in descending order. It's got the most positive reduction potential at the top, and then it goes down to the ones that are negative. What element has a reduction potential equal to 0? Hydrogen. Guys, hydrogen is considered our reference potential. Okay? Its cell potential is equal to 0. In this chart, guys, you'll notice everything above it has a positive cell potential, everything below is negative. Okay? I want to just call your attention to the word standard. Remember, that's what that little degree symbol means. Standard state. It tells you standard state conditions. It even says it in the title of the chart here, 25 degrees. Do you guys remember the pressure of standard state? 1 atm. Do you remember what the molarity is of anything in the aqueous state? 1 molar. Okay, those are standard state conditions. Okay, so we have this chart. Let's make sure that we get our bearings here. Okay, what are some questions I could ask you with this chart in front of you? And by the way, do you need to memorize anything? Absolutely not. Okay, if you need anything out of this chart on our next test, I will give it to you. Okay, but this is a reduction table. Okay, so when I say where are the substances being reduced, guys, we read reactions from left to right. Reduced. The charge is decreasing. I mean, just look down here at the very last one. Let's make it easy on ourselves. Lithium goes from a +1 charge to 0. Would you agree that that is decreasing? Yes. Okay. So where are the substances being reduced? We're looking at our reactants here. Which has the best reduction potential? Let me say that to you another way. Which of these reactants is its reduction potential? Are you ready for this? I'm going to make a tie-in from a long time ago. Which one of these reductions is the most thermodynamically favored? That came from a long time ago. Okay? Do you know how to answer that? The one that is the most positive in its potential. So what element is that? Fluorine. Fluorine gas is the most favored, the most spontaneous reduction on this chart. Okay? Now that wasn't so hard. Now I'm going to ask you to kind of bend your brains around a little bit. These are all written as reductions. How would you turn them into oxidations? Flip them all around. Okay? So, first thing I'm going to ask you to do is imagine this entire chart with every reaction written in reverse. Okay? What do you think happens to these potential values when you flip one around? It changes the sign. Okay? So, use your imagination here. Not only do I want you to imagine this whole chart with all the reactions written backwards, but all of these numbers are opposite in sign. Which, either element or ion, either one, is the best, the most favored at being oxidized? Lithium solid or lithium ion? Which one? Solid. Okay? You flip this reaction around, and then this now becomes the most positive potential in the chart. Lithium solid is the most favored to be oxidized in that chart. Okay? So positive potential means very favored, very spontaneous. So what else are we going to use this chart for? Well, here's what we're going to use it for. Okay? I give you an electrochemical reaction that looks just like that. And the question is, what cell potential will that galvanic cell have? How many volts can I get out of that battery? Here's what we're going to do. We'll do this together. If you would please, in this chart in front of you, find the half reaction that involves zinc solid and zinc +2. Find it. Okay. if you would, look in this chart again, find the half reaction that involves copper plus 2 and copper solid. Find it. Put your finger on it. Okay, fantastic. But I got a problem here. These are redox reactions, not read-read. How do you turn a reduction into an oxidation? Flip it, okay? Which one should I flip? Why the zinc? How'd you know that? Where are you looking? Okay. Most of you saw that zinc solid is a reactant, and right now it's not, so this must be the one to flip, and you're right. So I'm going to rewrite that flipped around. And what happens to the reduction potential, which is now an oxidation potential? What do I do? Yeah, just change the sign, so now it's positive 7.6. I'm going to scribble through this first one because I don't need it anymore. Okay. And I'm going to add these two guys together. Is there something I can cancel out? Okay, the electrons, and they have to cancel out. We'll talk in a minute about what happens if it's not the same number. We've actually done that before. All I have to do to get the total cell potential is really simple. All I do is add these numbers together. And that's it. Yeah. So how did I know to flip this one? Because I could see in the overall reaction, for example, that the zinc ion was on the product side, and right now it wasn't, so I knew I had to flip it around. And that's all there is to it. Now, what if, because we've done this before, so this is review, what if this wasn't so nice and tidy, 2 and 2? What if this was 2 and 3? Multiply the top equation times 3 and the bottom one times 2. Your electrons must cancel out. Okay? So that was a really simple one, but that's what you use that table for. Let's do one more together, because I want to show you something. This chart that you have in front of you is very helpful, but it's very small. It's limited. There's a bigger chart in the back of your book. Go to page, if you would, 1064. Go there. The chart on page 1064 in the appendix here is just a slightly larger chart. Please notice in this particular chart, the potentials are not in descending order. They are in alphabetical order by element symbol. Okay? So here's what I want you to do. Okay, because we're going to do number 1 on this slide together. The first half reaction that I want you to find in this chart involves chromium with a +3 charge and chromium with a +2 charge. Find that reaction. Chromium +3 and chromium +2. Okay. The other one I want you to look for involves magnesium metal and magnesium with a +2 charge. Find it. Magnesium, not manganese. Okay, now guys, please understand, all I have done is just copy straight out of the chart. I didn't have to really think about anything. Okay? Now, I can see right now, both of these are reductions, and I know that I'm going to have to flip one of them. Now, for those of you that have the PowerPoints, you have what's called the skeleton, kind of a skeleton equation. But let's say I didn't give that to you. How would you know which one to flip? Are you ready for how you will know? Once you have flipped one of your reactions, and you add your potentials together, your cell potential, the total, this plus this equals, your total cell potential must be positive. So after I flip one of these and I add my two potentials together, the total must be positive. Which reaction do I need to flip? The second one, the magnesium. You're absolutely correct. So I'm going to write it flipped. And tell me one more time what happens to that potential. Becomes positive, changes sign. Okay, I'm going to scribble through this because I don't need it anymore. Am I ready to add my two half reactions together?
Yes.
Why not? The electrons don't match up and they have to. So how do I fix that problem? Okay, let's multiply the top equation times 2. Am I okay now? Yeah. Now, wait, stop. I should have said this right off the bat. I multiplied that whole chromium half reaction times 2. Guess what? This remains unchanged. What do you call, think Chem 1, what do you call a property that you increase its amount, but that property remains unchanged? Intensive. Intensive. Potential is an intensive property. That makes things nice for us. We don't have to change that number. Here's my final balanced equation. That skeleton equation I gave you on the slide was not balanced. And there we go. Now, just to keep some perspective here, guys, if I were to link these two reactions together, I've created a battery. I'm going to get 1.96 volts out of that. Do you think I could power a remote control car with 1.96 volts? No. And I certainly couldn't power a real car. If changing the amount has no effect on your potential, how do we have batteries that put out many more volts than that? I think you guys are all thinking along the right lines. I mean, I can't just simply add more material because that's not going to have any effect. But what if I set up a second galvanic cell exactly like this one? Wouldn't I then get double the voltage? So what you have, guys, in any kind of real battery that we use in our everyday lives, you don't have one galvanic cell. You have many, many, many galvanic cells that when you add them all together, you get a lot of volts. Okay. All right. You guys do numbers 2 and 3 on your own. If you can't find a particular reaction that you're looking for in the back of the book, you might find it in that smaller chart. So you may have to kind of be flipping back and forth. Sorry about that. That's why I have a little playing card holding my place. Try these. Yeah, I tried to be as neat as possible.
I did it.
All right, so guys, as I said, the only thing that must cancel out is your electrons. Anything left over, like waters, H pluses, it's okay that they are there. In fact, they should be there. Okay? Now, is this a particularly productive galvanic cell? No, not so much, but it's putting out a little something. So that's number 3. So guys, here's the thing. And I sort of started to hint at this a little bit, but I want to make sure that this concept is now very, very clear in your minds. Why do we always have to flip one of our reactions? Why do we have to do that? To turn one of the reactions from a reduction into an oxidation, okay? And when we add them together, I said, we flip that one so that we can get a positive cell potential. Well, guys, the reason we do that is because a galvanic cell will only run spontaneously, meaning without any outside intervention. A galvanic cell will only run on its own if the cell potential is positive. Okay? If your cell potential, the total, comes out to be negative, then that's a battery that's not going to run on its own. So we're going to use this chart to answer some questions that you would likely see in multiple choice, because you don't need a calculator for this. All right, it says, is cadmium metal solid capable of reducing zinc ions? Okay, well guys, let's make this simpler than that. Take out the word reducing. How about just, will cadmium spontaneously react with zinc plus 2? Find, please, in this chart, find cadmium solid. Find it. Just to make sure that we are looking all at the same half reaction, what is its reduction potential? Negative 0.403. Okay. Tell me this, guys. Is solid cadmium in that reaction, is it on the reactant side? Yes or no? No. Well, it has to be. If I am asking you, will this react with that, that means it needs to be on the reactant side. So how do I fix that problem? Okay, flip it. What happens to that number, negative 0.403? Becomes positive. Okay, great. Keep that in your mind. Don't move your finger. Find zinc plus 2. Find it. It's the very last one. Is zinc plus 2 on the reactant side? Yes or no?
Yes.
Yes. And it needs to be. Now look at its number, negative 0.763. If you take that number and add it to cadmium's positive 0.403, what kind of a result do we get?
Negative.
Negative. Will this happen? No, it will not. If you get a negative cell potential, the answer is no, it will not. Is cadmium capable of doing that? No, it's not. Let's do another one. Just phrased differently, same situation though. Will an electrochemical reaction involving iron metal, stop there, find it, iron solid, is it on the correct side? Remember, it's got to be a reactant, is it? No, so you've got to flip it. Okay? It's going to change the potential to positive 0.44. Okay, keep your finger there, don't move. Solid iodine, find it. Is solid iodine on the correct reactant side? Yes, so I don't have to change that one. Now, let's think about what the total is going to be. Are we going to get a positive total, yes or no?
Yeah.
Yes. So will this reaction occur spontaneously? Yes, it will. Because our total is positive. Let's do one more. Barium metal. Find that first. Solid barium. Ask yourself, is it on the correct side? Is it a reactant? If it's not, then flip it. If it is, then leave it alone. So tell me what you think about this one. Yes. Why? Why is it yes? You get a positive total cell potential. You got it. Very good. Okay. So guys, let's kind of bring everything together that we've done today. If you are asked for a complete description of a galvanic cell, of a battery, there are multiple things you can now tell me. We just did some practice problems 2 slides back. I could give you a chart like this, and you could come up with a balanced reaction. You could tell me a total cell potential for an entire galvanic cell. Many times, especially, well, only in free response, it is very common. College Board will give these diagrams of a galvanic cell, and they will ask you to draw things into the diagram, like draw an arrow indicating which direction electrons are flowing. What did you write down in your notes earlier? Electrons always flow from anode to cathode. And that's something else you might be asked to label in a diagram. Okay? Remember, look back at your notes. Anode, what kind of reactions take place at the anode?
The oxidation.
Oxidation. Guys, isn't that the one that we always flipped? Didn't we flip one to turn it from a reduction into an oxidation? Make a note to yourself. The half reaction that you flip is always your anode. Write it down. Your half reaction that gets flipped is your anode, because you flipped it to turn it into an oxidation. So this is your final task for the day. I've made it easy for you. You don't even have to look these up in the chart. They're here for you. Give me a balanced equation, a total cell potential, and I know we don't have a diagram to draw an arrow in, but at least tell me which half reaction is your anode, which one is your cathode. Go. Number 1 was the slightly simpler, more friendlier one. Are we ready for number 2?
Yes.
If you're not, just don't look up.
Bring it. So happy. Wait, what happened to, the 60 split on the other side.
Ladies and gentlemen, in this problem, you can see, obviously your electrons always have to go, but sometimes you can cancel other things out as well. In this case, we were able to get rid of some of the water and some of the H+ ions. You can do that. If you can cancel things out, do it. It doesn't change the number at all, but okay. All right, I'm going to stop there.
Right.